Today's lesson is on inverse functions. In our textbook, if you had one, you will get one. It is chapter 1-5. And you studied inverse functions in Algebra 2 last year, so a lot of this is a little bit of a review. So by interchanging the x and y coordinates of ordered pairs, that just means switch x and y, of a function. In other words, switch x and y. You form the function's inverse. And the notation for an inverse is f, and then in the exponent position there's a -1, but that doesn't mean f to the -1, it just means f inverse of x. That's the notation. You should be familiar with that. Graphically, it's reflecting over the line y equals x. And algebraically, we can show the two functions are inverses of each other, or prove that they're inverses, which we're going to have to do. Show two functions are inverses by doing a composition of the two of them. And what a composition of them means is if you take the original function f, and if you compose that with f inverse of x, or another way of saying that is using the little O symbol for composition. So if you do f of f inverse of x, you should get in the end the variable x, and you have to also show that that the inverse in composition with the original function is also equal to x. And we're going to show that with a couple of examples. For example, let's say our original function, we'll just pick a simple linear function, f of x equals x plus 4. If I wanted to find the inverse of this is the same thing as y equals x plus 4. So if you switch the x and y, you get x equals y plus 4. And to solve that for y, you would subtract 4. So y equals x minus 4 would be its inverse. So we're going to prove that these two functions are inverses of each other algebraically. And in order to do that, in order to prove their inverses, we're going to show that f of f inverse of x is actually equal to the variable x. So to do f of f inverse of x, we take the original f function, take the x out, and replace or substitute that x with the f inverse function. So that would be x minus 4. There's the inverse function substituted for that x. And then you have to add 4 at the end. And if you simplify that down, you'll get x. And that's the first half of our proof. And the second half of our proof is to do f inverse of f of x. So you take the f inverse function, he's called the outer function, and you replace the x variable with the f of x function, x plus 4. So that would read x plus 4, and then you subtract 4 at the end, and if you simplify that expression, it simplifies down to x, and you've proven that x plus 4 and x minus 4 are inverses. The next example is a little bit more complicated. I'm going to choose a cubic function for my original function, 2x cubed minus 1. And if I wanted to find the inverse of that function, I would substitute y in for f of x. Y equals 2x cubed minus 1. Then I would switch x and y and get x equals 2y cubed minus 1. And then to solve that for y, I'd have to add 1, divide by 2, and take the cubed root to get rid of this. So it would be a 3-step process to solve that for y once you switch x and y. And if you've done that algebra, you will get the cubed root of x plus 1 divided by 2. And we're going to show, or we're going to prove that these two are inverses. Prove their inverses by showing f of f inverse of x and then f inverse of f of x. So we take the outer function f of x, we substitute in for this x value the cubed root of x plus 1 over 2. So that'll be 2 times the cubed root of x plus 1 over 2 to the third power minus 1. If you cube a cubed root, it gets rid of the radical, and you're left with 2 times x plus 1 over 2 minus 1. And these 2's will cancel out, and you're left with x plus 1 minus 1, which is equal to x. So there's the first half of the proof. And the second half of the proof is to do f inverse of f of x. So in the f inverse function, you take away that x and you replace that x with 2x cubed minus 1. So we're going to take the cubed root of 2x cubed minus 1 plus 1 all over 2. Minus 1 plus 1 cancels out to 0, and you're left with 2x cubed over 2, the cubed root of that. These 2's will cancel, and you're left with the cubed root of x cubed. And the cubed root of x cubed is just x, so there's your final proof in the end. So that's the algebraic way of showing that two functions are inverses, or proving two functions are inverses of each other. And graphically, if you want to show that they're inverses, you just want to show that for every xy pair in the original function, there's a yx pair in the inverse function. So that's the graphical proof. To show f and f inverse are inverses, then for every xy in the original function, there is a pair called yx in the inverse function. And I'm going to show you that on the graphing calculator. So I'll just pick a simple parent function, y equals x cubed. And the inverse of x cubed is the cubed root of x, so math, option 4, the cubed root of x. And if you take a look at the graph, there's your cubic function, and then here's your cubed root function, and you can see that they are reflections of each other across this line y equals x, so this is just a visual check on it. And then if you want to look at the table of values to get a numeric check, for every point here's the original function, x comma y, 0 comma 0, then y comma x, or y comma x is also in the function. So the original function has 0.00, 11, 28, 327, 464, which means the inverse function should have the 0.00, 11, 82, 27, 3, 64, 4. So we're just going to run through a few of these x values here. And 0, 0, 1, 1 are the same, but we're going to look to see if 8, 2 is on the table of values. So we'll go down to x equals 8, and 8, 2, this ordered pair, is on the inverse function. The next one was 27, 3, so we're going to look at x equals 27. and 27.3 is on our